All right, let's get started, guys. We're in section 5.4. And we're talking about the Pythagorean Theorem. Okay, so we decided when we were talking about what we already knew, that the Pythagorean theorem is for right triangles. And the sides of our triangles, sides A, B, and C. And C is the hypotenuse. And remember, the hypotenuse is the longest side and it's opposite the right angle. C is the hypotenuse. The Pythagorean theorem tells us that a squared plus b squared equals c squared. And let's draw a triangle here so we can label it. There we go. Here's our right angle. C is opposite the right angle. So it's across the triangle from the right angle. And A and B, it doesn't matter what order I put A and B on the right triangle. Either of these two sides could be A or B, but C always has to be the longest across from the right angle. So this is the Pythagorean theorem. The Pythagorean theorem has been around for a long time. They in the book it talks a little bit about it. In Iraq, what used to be Babylon, they found a stone tablet, or a piece of a stone tablet, and the tablet had columns of numbers written on it. And for a long time they couldn't figure out what it was, what it was talking about. And then a mathematician looked at it and he said, "Oh, these are sides of right triangles. These numbers work in the Pythagorean theorem." So, and this was from around 1700 BC that this stone tablet dates from. So, as far back as 1700 BC, people knew this relationship with right triangles. Then it would be more important to keep track of land and where the boundaries of the land are. So that's why they would calculate these things. But they figured this out as far back as 1700 BC. They have similar things written in ancient China, where the Chinese knew about the Pythagorean theorem, that it worked that certain numbers would work to make a right triangle. So it's something that's been around for a long time. Pythagoras was kind of made the Pythagorean theorem famous, so that's why it ended up with his name on it. But it's been around for almost as long as civilization. That when humans started kind of.
But when did we know?
When did we know?
Yeah.
Well, Pythagoras was in ancient Greece, so that's I can't remember exactly when he dated, but that's kind of around. I'm thinking like in the 200s something. Off the top of my head, I'm not for sure. But so we've known about the Pythagorean theorem for a long time, as we wrote it down here. So let's look at a couple of examples of how we'd have to solve problems with the Pythagorean theorem, and then I want to give you, and we'll talk about a couple different pieces of the Pythagorean theorem, and then I want to remind everyone about simple radical form, because we're going to be doing a lot with square roots. So let's look at an example, just calculating with the Pythagorean theorem. So here's my triangle. I'm going to say that side's 15. This side is 34. And we want to find the missing side. Now what I suggest you do when you have a Pythagorean theorem problem to help you keep your numbers straight is label your sides. So on this triangle, which side is going to be C? The question mark. That's what we're trying to find, C. And the other two, it doesn't matter. I'll just call this one A and this one B. That helps us remember where to put them into our formula. So here I'm going to say 15 squared plus 34 squared equals C squared. If I calculate this out, 15 squared is 225. 34 squared is 1156. And that equals C squared. Add these two together, I'm going to turn my equation around. C squared equals 1381. And to solve this, what do I have to do? Square root. So take the square root of both sides. When I do that in my calculator, I get C is about, if I round it off, 37.16. And my units, we're talking about length. So that'd be 37.16 units. So this one was pretty straightforward. I just plug my numbers in and calculate. Let's look at where we have to solve for a different part of the triangle. So on this example, here's my triangle this time. And we're going to say that this side is 3, this side is 4, and this side is a question mark. And we want to figure out this side, and we know this is a 90-degree angle. So on this triangle, which side is going to be C? 5. And it doesn't matter A or B, I can put those either way. So let's write our Pythagorean theorem with what we have here. A squared is 3 squared plus B squared is what we need to figure out, equals 5 squared. 3 squared is 9 plus B squared is 5 squared is 25. Subtract 9 and I get B squared equals 16. Take the square root and B equals 4. When we have 3 integers, like 3, 4, 5, numbers like 1, 2, 3, whole numbers, when we have 3 integers that make the sides of a right triangle, they're called Pythagorean triples. So 3, 4, 5 is one that you'll see often enough that you'll probably start to remember that 3, 4, 5 will always make a right triangle. It's a pretty common set of side lengths for Pythagorean theorem. Questions on the Pythagorean theorem so far? All right. Let's look at the next part. The next little piece of information that we're talking about with the Pythagorean theorem. The converse. Converse of the Pythagorean theorem. So what we said on the last page is if we have a right triangle with sides A, B, and C, then A squared plus B squared equals C squared. Now we want to make the converse. What do we do for the converse? Do you remember how we make a converse of an if-then? What is it? Flip it. We turn it around. So our converse is going to say if A squared plus B squared equals C squared for a triangle with sides A, B, and C, and C is the longest, then the triangle is a right triangle. Yeah. So the converse tells us if we know three sides, if we know the three sides of a triangle, if they work in the Pythagorean theorem, then we know that the triangle is a right triangle. So our hint when we work on problems like these, when it says something about a right triangle and you have the sides of a triangle, that should be your clue that you're talking about the Pythagorean theorem. Right triangle, the first thing you should think when you see right triangles, you should think Pythagorean theorem. Because if you remember, at the end of last semester, we did some problems where we had three sides and we wanted to figure out if we could make a triangle with those three sides. We had three sides and we were trying to figure out if we had a triangle. This problem is a little different. When it says right triangle, we think, does it work in the Pythagorean theorem? And we'll give one more set of rules, and then we'll do some examples using the converse and the next piece of information that we talk about. So we have the converse of the Pythagorean theorem tells us when we know the sides, can we figure out if it's a right triangle? And we also want to talk about the Pythagorean inequalities. The Pythagorean inequalities tell us if we don't have a right triangle, what kind of triangle do we have? Acute or obtuse? So we have three possibilities now. So we have a triangle, triangle ABC, and C is the longest side. If, and this is what we just talked about, if c squared equals a squared plus b squared, then the triangle is a right triangle. And if we want to draw a little picture, I could draw a little picture like so. That would be my triangle. So if we know that c squared equals a squared plus b squared, we know we have a right triangle. Our second possibility, if c squared is greater than a squared plus b squared, then what kind of triangle do you think we have? We have an obtuse triangle, that's correct. And if you want to draw a little picture, an obtuse triangle is going to look like this, where this angle is bigger than 90 degrees. And we have the last possibility, if c squared is less than a squared plus b squared, then what do you think we have? Acute. And an acute triangle is going to look like so. So all the angles are less than 90 degrees. So those are our three possibilities with the Pythagorean inequalities. If it's equal, if it's exactly the same, we have a right triangle. If c squared is greater, then we have an obtuse triangle. And if c squared is smaller, then we have an acute triangle. Any questions on the formulas? Let's look at a couple of examples using the converse and using the inequalities. So for all of these, we're trying to figure out what kind of triangle. So for the first one, we have sides 14, 7, and 9. And we want to figure out what kind of triangle. So let's label our sides. Which side of these three is going to be C? 14. The other two, it doesn't matter. I can call either one A or B. So here's C, A, and B. So let's see if this works in the Pythagorean theorem. Again, our clue here, we want to see, does it work in the Pythagorean theorem? So a squared plus b squared is 7 squared plus 9 squared. And that's 49 plus 81, which, when I add those together, I get 130. C squared is 14 squared. And when I square 14, I get 196. So C squared is greater than a squared plus b squared. So what kind of triangle is this? This is obtuse. Let's look at another possibility, another example. In this one, we have 2.5 for our side, one side, 6, and 6.5. We want to know what kind of triangle. So for this one, which side is going to be C? 6.5, our longest side. Call these other two A and B. So let's do a squared plus b squared. 2.5 squared plus 6 squared is 6.25 plus 36, which is 42.25. And c squared is 6.5 squared, which is 42.25. So what does this tell us? It is a right triangle. Because it's exactly the same, because it's equal. A squared plus b squared equals c squared. So this is a right triangle. Let's look at one more example. Our sides are 2, 3, and 3.5. Which side is C here? 3.5, the biggest. I'll call this one A and B. So 2 squared plus 3 squared is 4 plus 9, which is 13. 3.5 squared is 12.25. So c squared is less than a squared plus b squared. So what kind of triangle do I have here? Acute. And the one way that helps me remember is if I put my hands, make a triangle with my hands. If I have a right triangle, c squared equals a squared plus b squared. If c squared is bigger, I have to open my hands up wider. So I have an obtuse triangle. If c squared is smaller, I have to close my hands down further, and I have an acute triangle. So I have right, if c squared equals a squared plus b squared. Obtuse, I have to open up further. Acute, I have to close down a little bit. So that helps me to visualize how they work. Any questions on what we've done with the Pythagorean theorem? Yes? All right. Let me give you a quick reminder, because we're going to, some of the problems we'll start asking you in the homework to leave your answer in simple radical form. So let me remind you what simple radical form means. This is something that, that you talked about last year, but you might not have, probably didn't think about it much since then. When we want simple radical form, we want to leave a square root in our answer. So an example would be if we had something like the square root of 12. And we want to put this in simple radical form. So we don't want to put it in our calculator and get a decimal. We want to simplify this a little bit. So what I do is I write square root of 12. I want to factor 12 into factors that where one of them is a perfect square. So 12 is 4 times 3. And now I can separate the square roots. And square root of 12 is the same as 2 times the square root of 3. I separated 12 into 4 times 3. The square root of 4 is 2. And 3 I just leave because I can't take the square root. 3 is not a perfect square. So I leave it written as 2 square root of 3. If I had square root of 32, 32 is 16 times 2. Square root of 16 is 4, so that would be 4 square root 2. So this would be simple radical form. Let me do one more, and we'll work with this a little more. I just wanted to remind you what simple radical form means. Square root of 50. 50 is 25 times 2. Square root of 25 is 5. And I leave this. So all of these are examples of simple radical form. So I think there's one problem on the homework that asks you to leave your answer in simple radical form, maybe two. And we'll do more with this as we go on, simplifying radicals, because with the Pythagorean theorem and the next topic that we're going to talk about, this will come up more. All right, any questions? Okay, let me pass out the